In this video, we'll be going over some notes for Experiment 8, in which we're determining experimentally the value of the gas constant R. So we know when we're thinking about gases, we usually use the ideal gas law, which says that PV is equal to nRT, where pressure is P, V is the volume, N is the moles, and T is the temperature, all of the gas that we're interested in. And if we rearrange this equation, we can solve for the gas constant R and say that it's equal to the pressure times the volume over the moles times the temperature. So in order to be able to solve for the gas constant R, we need to obtain information about our four variables, pressure, volume, moles, and temperature, from a reaction. The reaction that we're looking into is the decomposition of hydrogen peroxide into water and oxygen gas. And this reaction happens naturally, but it's quite slow, so in order to do it in lab, we're going to speed it up by adding yeast. We also want to make sure our equation is balanced so we can think about what's actually happening. So because the ideal gas law is true for a gas, we'll be measuring the volume, pressure, temperature, and moles for the oxygen gas formed in the reaction. Now let's go over how we're going to figure out all of the information about these variables under our reaction conditions. So to figure out T, the temperature of our gas, what we're going to do is just record from a thermometer what the temperature in the room is. Because we know that the reaction is done at room temperature, but we just have to know that we're going to take our temperature in Celsius and convert to Kelvin. In order to get the temperature in Kelvin, all you have to do is take the temperature in Celsius and add 273.15. Since we're doing addition, you want to keep in mind how many decimal places you can have from this calculation. Our next value is volume. To figure out the volume of the gas, we have to think about how the reaction is set up. So, in order to do this reaction, what you're going to do is have your little container of yeast in your solution of H2O2. When you tip over the little yeast cap, what will happen is that oxygen gas will start to form. So as the reaction happens, oxygen forms and it will go up through this tube and into the next container where it will displace water from our Florence flask. So it will go in here and oxygen will be displacing the water in the middle flask. As the water is displaced, it will go up through this tube and into our beaker. So this is where the water is collected, and we will measure this volume in a graduated cylinder, which we'll measure in milliliters. And so the volume of water that's collected is going to be equal to the volume of oxygen that is formed in the reaction. Okay, so now we've got temperature and volume. Let's talk about pressure. So, at the start of lab, your instructor will tell you the barometric pressure or the atmospheric pressure for the day, and that's from a barometer. And so your instructor will give you this information. Let's think about all the pressures that are acting on the different flasks in our reaction setup. So, if something is open to the air, then it is under atmospheric pressure. In our flask at the left, we are just thinking about the pressure of oxygen because that is what's forming in that flask. The middle flask has some pressure from water evaporating and also from the oxygen that's forming and getting transferred into that one. At the end of the experiment, we're going to raise our beaker so that these two pressures are equal. And so we know that the atmospheric pressure, or the total pressure, is equal to the pressure of our gas that forms plus the pressure of the water that evaporates. And so if we want the partial pressure of oxygen, or just the pressure of oxygen by itself, we'll take the atmospheric pressure that we were given minus the pressure of water. And we can get this from the table. Okay, so you're going to use T, the temperature from above, in step 1, okay, and figure out what the pressure of water is at this temperature. And so the pressure of oxygen we'll find in millimeters of mercury, but we'll be able to convert this to atmospheres using a conversion factor, because we know that 760 millimeters of mercury is equal to 1 atmosphere. All right, now we have 3 of our variables. The last one is N, or moles of gas. The way this reaction is set up is that what we're going to do is have our Florence flask, and it's going to contain H2O2 solution. And it's going to contain our little cap full of yeast. We are going to measure the mass of this solution before we shake it or start the reaction. Once the reaction goes, the yeast will be all kind of spread out on the bottom. We'll have our little cap, and we'll still have some liquid remaining here. But what happens is all of the oxygen has left. And so if we measure the mass after we do the reaction and take the difference, the mass before minus the mass after, completing the reaction and waiting 10 minutes, is the mass of oxygen. And if we know the mass of oxygen and divide by the molar mass of oxygen, we will get the moles of oxygen. So let's look at our data sheet so we can see how these are filled in. So room temperature C is what we had for T above. We'll just fill that in from a thermometer. This barometric pressure is our atmospheric pressure, and we record it from the barometer, and it should have units of millimeters of mercury because this is our data that we're just measuring. None of this is yet calculated. You'll also then use this temperature to figure out the vapor pressure of the liquid at room temperature, so you'll use the table that's provided. This also has units of millimeters of mercury. Then, once you are finished with the reaction, you will measure the volume of oxygen evolved, which is equal to the volume of water in the beaker after a reaction, and this will have units of milliliters. So that's just our raw data. Now we'll be able to do some calculations. Since we have our room temperature in Celsius, we can get our room temperature in Kelvin by adding 273.15. So now this unit will be in Kelvin. For the volume of oxygen evolved, we're just going to take our volume from here, and we're going to divide by 1,000 to get the volume in liters. For the mass of oxygen evolved, we're going to do a before minus an after to get the mass in grams. And then to get the moles, we will take the mass of O2 divided by the molar mass of O2 to get the value in moles. The partial pressure of oxygen evolved, as you saw up above, is the atmospheric pressure minus the water pressure from the table. That will give you the pressure of oxygen, and in this part has units of millimeters of mercury. Once we take the millimeters of mercury and convert to atmospheres, so it's the same value, we're just converting to a different unit. Okay, so now we have units of atmospheres. So then our goal is to solve for R, and as you saw above, if we rearrange the ideal gas law, R is equal to PV over NT. So you're going to plug in the appropriate units here so that you end up with atmospheres times liters over mole Kelvin. And then percent error, if you recall from earlier experiments, if your instructor is asking you to do this, this will be the calculated minus the accepted as an absolute value over the accepted times 100%. And be sure you're paying attention to significant figures here, because with subtraction you often lose significant figures. The next part of this sheet is going through and determining the percent of peroxide by weight. In this experiment, the peroxide that we're using is sold as a diluted solution. So we have some peroxide in a large amount of water. So we want to figure out also how much of it was peroxide and not just water. And so in this table, the mass of H2O2 solution we'll find with step 3 below. The mass of H2O2 consumed you'll see from step 2 below. And the last one is step 4. So let's take a look at how we're doing this. So we can think about, based on how much oxygen we made, how much hydrogen peroxide had to be in the solution to begin with. So step 1, it says use the mass of O2 to find the moles of O2. So we've already done that because we used the mass of oxygen to find the moles for our R value calculation. So we know that 1 mole of oxygen has a mass of 32 grams. So this gives us 0.00872 moles of oxygen. We're going to use the balanced equation that we wrote earlier to figure out how much H2O2 was in there originally. So if we take the moles, we can write a mole ratio. So we know that 2 moles of hydrogen peroxide were in the solution for every mole of oxygen that were reacted. Then we can use the molar mass of just the H2O2 to figure out how much of that was in the solution to begin with. And in this calculation, we get 0.593 grams of hydrogen peroxide. The mass of the H2O2 solution can easily be found if we take the mass of our flask plus H2O2 solution and subtract the mass of the flask by itself. So let's say, for example, that the mass total was 70.495. You'll just record whatever value you got in lab. And the mass of the flask by itself was 51.559 grams. When you subtract these two values, you get 18.896 grams of H2O2 solution. So if we know how much was pure H2O2, and we know how much was of the solution, then we can find the percent by weight. So the mass of solute was from step 2, the mass of solution was from step 3, and then we multiply by 100. So we get 0.593 grams divided by 18.896 grams times 100%. And so for this particular example, I got 3.14%. And your value should be similar to this one. And that's all you need to know for experiment 8.